Hello everyone, here we'll be discussing Green's theorem. And Green's theorem is this theorem I have written here, and it says it's kind of a huge crazy setup first, so just bear with me. So first we want to let C be a positively orientated, piecewise smooth, simple closed curve in the plane, and we want to let capital T be the region bounded by C. So it's kind of a strange sounding setup, but to be quite honest, it's a pretty common setup, and I'll show you that in a moment, what it looks like. If P and Q are functions in, let's say, two variables x and y, and they have continuous partial derivatives on an open region that contains D, in other words, we at least need their partial derivatives to be continuous in all of D, is what this is really saying, then this is true. And this is the formula for Green's theorem. And it says that the line integral along the curve C of PDX plus QDY, we've seen this a lot before in previous videos, is equal to the double integral along over the region D of this quantity, which is the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y dA. Now first off, this whole business, positively orientated, piecewise smooth, we've seen that. Simple curves, we know what those are. Those are curves that don't intersect themselves. So what this image should remind you of, or what should come to mind, at least what comes to mind for me, is something like this. So we have a closed curve, meaning that there's no loose ends, so to speak. It kind of encloses a region, basically. Its endpoints are coincident, they're the same. Okay? And positively orientated, well, if you think about how we usually orientate circles for trigonometry, for instance, or angles, that is, that's in a counterclockwise fashion. So this is a positively orientated curve if the arrows are going in the counterclockwise direction. Otherwise, it's negatively orientated. So this curve is C. Okay? The region that this encloses is D. So let me kind of like shade around that so you know that that's what I mean. So the whole region, the whole solid region, shaded region, is D itself, but the boundary of D is the curve C. And in fact, there's actually notation for this. So here we can say that C is actually equal to partial D, and here this means boundary of D. Okay, so it's just the outside curve of the region D. Okay? All right, now piecewise smooth, we saw what that means. We've seen what that means before, is that it's not necessarily all smooth, but it can be broken up into smooth pieces, or smooth subsections, if you will. So here I made it look like it kind of has a sharp point here, and that's fine, as long as it doesn't have infinitely many sharp points, so to speak. So you can break it up into sections where each of those sections are smooth. That's what piecewise smooth means. Now why smooth is a thing, why that's important, is because if a curve is smooth, that basically means that its derivatives exist along that smooth, so-called smooth part of that curve. All right, I think that's all I wanted to say there. There is also a different notation that could possibly be used. So here, this is line integral along C. That's fine, that's kind of what we've been seeing in previous lessons. But something that can alternatively be used is this circle notation. Now this is a line integral along C, but the circle means it's over a closed region C. So this just tells you that C is closed. From previous lessons that we saw, we didn't actually need C to be closed, but sometimes it was, sometimes it wasn't. Also, there may be an arrow on it's kind of hard to tell, but I'm trying to draw an arrow here on the circle, part of the integral, telling me that it's a positively orientated. So this describes line integral along a positively orientated closed curve. That's all that means. Awesome. I kind of went a little bit out of frame. Let me scoot that over a little bit so you can see that. There we go, looks a little better. And right, so I'm going to do an example in a moment. I don't have space to do it right here. I want to erase this and throw an example up. But before, let's kind of look at what this says. So we have two functions. One is multiplied to dx, one is multiplied to dy. And notice here we turn it into a double integral according to this theorem, but these reverse and you get subtraction. So when I say the reverse, basically q is in the x kind of location and p will now be in the y location, meaning that we always write x first then y. So if you swap them, then that means we're taking the partial derivative with respect to x of q and then with respect to y of p. So notice the kind of asymmetry there, okay? So with that being said, I think it's okay for us to now jump into an example. I'm not going to prove Green's theorem by any means. It's pretty difficult to prove as it turns out. Now I'm looking at the book I'm using to kind of describe these things, and there is a proof that the book goes through, but it's actually super involved. As it turns out, it's a specific version of Green's theorem where the region is of a certain type, and then they prove that specific case. To prove it in general is way more involved, as it turns out, and the proof the book goes through is about a page and a half, and that's for the simple case. For the more general case, I'm sure it's pages, and we're not going to take our time. We're just going to take it as fact. But now let's look at this example now and see what that entails. Right, so for this example, we want to evaluate this line integral, which along the curve C is x to the fourth dx plus xy dy, where C is the triangular curve consisting of the line segments from 0, 0 to 1, 0, from 1, 0 to 0, 1, and then finally back from 0, 1 back to 0, 0. So just to describe what this triangular curve looks like, we have these points 0, 0, 0, 1, and 1, 0. Now it says specifically from where to where, so that describes an orientation. So from 0, 0 to 1, 0, that's this way. Then from 1, 0 to 0, 1 is this line segment here like this. And then finally from 0, 1 back to 0, 0, we have this closed curve. And that's how it's described. Now, I'm trying to see how we can break this up, but I'm actually not going to do that. Really what we want to do is we want to describe the region, not the curve. That's what Green's theorem does. It turns a line integral into a double integral about this region instead of the curve itself. It's positively orientated and curved, and closed. That was what I meant to say, closed curve. So, and it's simple, it doesn't intersect itself. So we have that part of Green's theorem down. Now what we need to do is we need to basically set up some labelings here. This will be our P from Green's theorem. This is then our Q. So that means that this integral, this line integral, will now be equal to the double integral along the region D, which is this shaded region here. Let's call that, point to that, call it D. And this is going to be of what? Remember, you swap them, subtract, and take partial derivatives in that location. So Q is now in the X location, so that's partial Q with respect to X, minus partial P with respect to Y, dA. So let's get that part right. So the double integral over D, derivative of this with respect to Y, with respect to X, drops the X, so you just get Y, minus derivative of P with respect to Y is just 0 actually, look at that, dA. So really this is just the double integral of Y dA. So that made that pretty simple, but now how do we describe this? Well, this is a type 1 region, and in fact, how we can describe this region D in this case is we can say that D is a set of all points x comma y, where x is in between 0 and 1, and the y values are in between what curves? Well, the lowest y can be is equal to 0, the highest y can be is on this line. It's kind of, I guess, I was going to say the ceiling is this line, so to speak, for each x value. So y is going to be in between 0 and this line. Equations of lines are pretty simple to do if you consider slope-intercept form. Think of this as y equals mx plus b. So y is equal to negative 1 over 1x, so it's negative x, plus the y-intercept is 1. So it's negative x plus 1 or 1 minus x. So I'm just going to write 1 minus x just because of space. That didn't cut off, good. So now with that being said, we can write this double integral now as the integral from 0 to 1, that's with dx, of the integral from 0 to 1 minus x, and that's going to be dy, of just y. So dy first, then dx. Perfect. Antiderivative of y is 1/2 y squared. If we evaluate that between 0 and 1 minus x, we end up with, well, when you plug in 0, you get 0. So that part's done. When you plug in 1 minus x, you get 1/2 1 minus x to the second power. So that means now we're going to take the integral from 0 to 1 of 1/2 times 1 minus x to the second power dx. This is actually pretty simple to do. Pull the 1/2 out. That's fine. Antiderivative of something to the second is 1/3, that's something to the third. So that makes this 6th actually, because 1/3 times 1/2 is just 1/6. But by chain rule, the derivative of the inside would be -1, so technically you have to divide by -1, making this a negative. And if you don't believe me, take the derivative of this and you'll see that's true. And if you have trouble doing that, really what I'm describing is a u substitution, letting the inside be u. So if you want to do it that way, you can, but I'm just doing it kind of quick like this. And that's not to be confused with this, that's from above. Okay, and now we're evaluating this between 0 and 1. Now, when you plug in 0, it's going to be 1 to the third, but when you plug in 1, it's actually going to be 0, because you'll have 1 minus 1 on the inside. So that cancels out, so we end up with a 0 minus -1/6. And actually it's just -1/6, because when you plug in 0, you get 1 to the third for this power part. And 0 minus -1/6 is just +1/6 then. Awesome. So the integration part I kind of just rushed over a little bit, but it wasn't too terrible, I don't think. But Green's theorem really saved the day as far as turning this line integral into a double integral that we've seen before when we discussed double and triple integrals. Awesome. So now I think I'm going to do a few more examples, and maybe I'll go over a different case for Green's theorem, a different, I guess, scenario we can talk about. All right, so here for this example, we'll evaluate this line integral. Remember, the circle here means over a closed curve, positively oriented closed curve, of this crazy thing. So it's a 3y minus e to the sine x dx, 7x plus the square root of y to the 4th plus 1 dy. Where c is the circle, x squared plus y squared is equal to 9. Again, this integral tells us that, the notation that is, tells us it's positively orientated. So I guess we can draw it, but x squared plus y squared equals any number is always going to be the circle centered at the origin whose radius is the square root of that number, in this case 3. So we have a circle with radius 3, something like that. And what we're going to do is apply Green's theorem. So I'm going to write gt on top for Green's theorem. So now this will turn into the double integral over the region D, which is just this circle itself, so that's D, of, so remember we swap these and then take derivative with those opposite locations. So derivative of this with respect to x is just going to be 7. Derivative of that with respect to x, this is a constant, so it's going to be 0. Derivative of this with respect to y is just going to be 3, because notice e to the sine of x, even though it's a nice looking function, in the eyes of y it's a constant, and its derivative is just, well, 0. Awesome. So now we have this, and that's dA. Now, this is kind of interesting because at this point, we just have a constant. This is just 4. And there are all sorts of ways to handle this. The way I honestly want to handle this is by pulling the 4 out, and then just saying, well, the double integral of dA over region D is just the area of D, which is one of our integral rules. So this is the area of D, and the area of a circle, the radius 3, is pi times the radius squared. 3 squared is 9, 9 times 4 is 36, so it's 36 pi. And I want to call it a day there. There are a few other ways of doing it that are kind of interesting that I think I kind of want to take a little bit of time with. So I'm going to say that we can also write this region as a type 1 region, as the region of points or set of points x, y, where x is in between -3 and 3, and y is in between the top part of the curve. In other words, if you solve for y, we've seen this before, subtract x squared, take the square root to get y by itself, you get y would be equal to positive or negative 9 minus x squared inside of a radical. So y is in between those two radicals, the positive radical and the negative radical, like that. So on the other hand, if you set this, so it would be at this point, I guess. So at this point you can set this up as a double iterated integral where we do y first, going from the negative radical to the positive radical, dy, and then from -3 to 3 dx. Alright, so now we have, again, 9 minus x squared inside this radical, just to kind of complete that. Now the antiderivative of 1, that's technically our integrand, with respect to y is just y, and then taking the difference of these, notice we'll have this radical minus negative itself. Because we evaluate y, which is the antiderivative of 1, evaluate that between the top and bottom. So plug in top into y minus plug in bottom into y. But since you have double negative, it's positive. So in reality, this is 2 times that. 2 times 4 is 8, so I'll pull that out of the integral from -3 to 3 of this radical dx. Now already here, this is actually pretty difficult to do. I mean, we could do this with a trig substitution, or we can just say, well, if you solve for y here, you just get the upper half circle, and the area of the upper half circle is just, well, that would be half of 9 pi, and in between -3 and 3, that is, and half of 9 pi times 4 times 8, well, 8 divided by 2 is 4, so that's going to be 4 times 9 pi, which is again 36 pi. So again, at this point, you can also do it visually. But if you want to see the trig substitution, I'll just show that real quick. We can do x is equal to, let's say, sine of theta. So the dx will be cosine of theta. And I think, let me see here. Yeah, it's actually not too bad. So if x is equal to sine of theta, then 9 minus we need a 3 in front of this. That's where I was kind of struggling with that. Why do we need a 3 in front? And I forgot d theta even. Why we need a 3 in front is that when you square this in the radical part, you get 9 minus this squared, which is 9 sine squared. If you have 9 minus 9 sine squared, you can pull the 9 out and get 9 times the quantity 1 minus sine squared. And there's a Pythagorean identity that says sine squared plus cosine squared is 1, so 1 minus sine squared is cosine squared. So this is 9 times cosine squared. Perfect. And if 9 is equal to cosine squared, then, if this inside is equal to 9 cosine squared, then take the radical of this, square root of this, we just get 3 cosine. But dx is cosine theta d theta itself, so this becomes 8 times the integral of 3 times cosine squared theta d theta. And again, why there's a 3 is because we take the square root of 9 to get 3. Why there's cosine squared is because when you take the square root of cosine squared, you just get cosine. But since dx gives another cosine, in fact, it gives another 3 as well. So it's 3 times 3, which is 9 then. And then that gives you 72. And this is still from -3 to 3. Well, not really, actually. Because at this point, you have to change the limits of integration. And you can kind of see, when x is 3, then sine would be 1. And sine is 1 either a pi over 2 or negative pi over 2. Yeah, it's a little tricky. I mean, it's still doable. I kind of don't want to continue doing it this way, because to take the antiderivative of cosine squared, we actually need another trig identity, which is 1/2 of 1 minus cosine, or I guess 1 plus cosine of 2 theta, and that's actually easier to take the antiderivative, but you can already see it's pretty involved. In this case, doing it visually, noticing that this is just an area of a circle, or in this case, area of a half circle, I think is fine enough. There is another method I wanted to show that involves using polar coordinates that I've done before in previous videos, but instead I'll do that for a different example. So let's take a look at one more example now. The region will be a little more complicated, and that I think will be okay to use polar coordinates on. So let's take a look at that right now. Okay, so for this next example, we want to evaluate this line integral over this closed curve, y squared dx plus 3xy dy, where C is the boundary of the semi-annular region D, and the upper half plane between the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. Now, semi-annular refers to half of what is called an annulus. And an annulus is just a circle with the inside missing. So imagine like a disc, or in this case, I guess it would be a washer. So, but it's a two-dimensional region. Otherwise, if it's three-dimensional, what comes to my mind is like a torus, or sometimes known as a donut, if you think about it. But, right. So specifically what's going on is that we have this inner circle of radius 1 centered at the origin. And then since the square root of 4 is 2, then we have this outer circle with radius 2 centered at the origin. Just like that. I think that looks good. So this is the region we care about here. And remember our notation, that circle in that integral right here tells me that we're positively orientated. So let me just kind of describe how that's positively orientated. So the outer part makes sense, it's just in the counterclockwise fashion. But this whole region, or this whole boundary, continues actually on the x-axis. So think of it like that. So these parts actually mean something, as it turns out. Okay, good. So that's describing the region. But now, really what we can do is we can just jump into Green's theorem, because it's positively oriented because of the notation. So by Green's theorem, what do we get? Hopefully we're pretty good at doing this by now, but now it's a double integral over the region D of derivative of this with respect to y, which is just going to be 3x. I'm sorry, with respect to x, because we're putting it over here. So that's going to be dropping the y, so that's dropping the x, so that's 3y. There we go. Minus derivative of this with respect to y, which is 2y. And in fact, 3y minus 2y is just y, and this is that dA. So this is the double integral of the region D over the region D of y dA. Now, again, we could describe this in such a way using a type 1 region, kind of. I guess you could do it with a type 1 region, but it's going to be a little weird. Instead, what I'm going to do, like I said I would previously, from the previous example, or at the end of the previous example anyways, is I'm going to actually attempt to do this problem in polar coordinates. So in polar coordinates, this region D can be described by the following. So it's the polar point r comma theta. So in polar, points are referred to as the radius comma their angle. So if you have a point on the xy plane, it corresponds to the angle that we're being lifted up and the radius we're going about to get to that point. Instead of its x and y coordinate to get to the point, it's angle and distance from the origin. That's what r and theta refer to. Where r is going to be in between 1 and 2, because those are the radius of the circles. So this region is where the radius of the point is in between 1 and 2 from the origin. And notice the angle, this is the upper half circle, so the angle's from theta equals 0 to theta equals pi. So from 0 to 180 degrees, basically. Perfect. So this describes the region in polar. Now the only other few things I have to show you, well, it's quite a bit, is that in polar, so let me just say for polar coordinates, there are a few things to notice, and that is that x is equal to r cosine theta, y is equal to r sine theta, I guess x squared plus y squared is equal to r squared, and that's true from the above two. If you square those, you just get r squared times the quantity cosine squared plus sine squared, which is 1. So we get x squared plus y squared is equal to r squared. There are a few other things, but that's all I'm going to say here as far as variables are concerned. But there's one more thing we actually need that's pretty important, and that's that the double integral dA will actually turn into dr d theta, r dr theta. So let me just say that dA is equal to r dr d theta. Okay, I put that in quotations because that's what we're replacing dA with. It doesn't necessarily mean that that's equal to that, but it kind of is equality. Okay, so with that being said, I think we're good to continue. So converting this to polar, now we can say this is the double iterated integral, where r is going from 1 to 2, theta is going from 0 to pi, y is being replaced with r sine of theta, dA is being replaced with r dr d theta, And we actually have a multiple of r and theta, and sine of theta in this case. So we can actually split this up into a product of an integral in theta only and an integral in r only. So that means this is going to be the integral from 0 to pi of sine theta d theta, which we'll do, times the integral from 1 to 2 of, I guess, r squared dr. Because notice we have two r's here that multiply to r squared. Perfect. Now the antiderivative of cosine, of course, is negative cosine. The antiderivative of sine is negative cosine, so that's kind of funny. Evaluate that between 0 and pi. Cosine of pi is -1, so negative cosine of pi is +1, minus cosine of 0 is 1, so that means negative cosine of 0 is -1. So we actually just get the number 2. Times, so that's this one, the antiderivative of r squared is 1/3 r cubed. Evaluate this between 1 and 2. We're going to get 1/3 2 cubed, which is 8/3. Minus 1 cubed is 1, times 1/3 is 1/3. So here we just get 7/3. So we have 2 times 7/3. So this is 7/3. So in total we have 2 times 7/3, which is 14/3. That's kind of interesting. But yeah, that's it. That's how you do that in polar coordinates. So it's a little different, something to possibly get used to. I don't think we're going to see this too often, but when we see it, it'll probably be in a simple case kind of like this. How you can recognize when it's I guess you can say when it's worth doing is when your region is circular. Kind of like we saw from the previous one, that was actually, we could have done that way. And from this one as well, we have this kind of circular region. All right, so now I want to look at something a little different. We're actually going to be trying to tie in vector fields into the idea of Green's theorem quite a bit. So let's take a look at that right now. Right, so there's a few things I want to discuss to kind of generalize Green's theorem a bit for some specific regions. And I guess specific curves or boundaries of those regions. But we have to recall a few things first. So recall that if you have this type of line integral that's p dx plus q dy over a negatively orientated curve C, this is equal to negative the integral over the positively orientated C. So here C is assumed to be a positively orientated curve, not necessarily closed, but possibly closed. Now recall that this is not necessarily true when it's ds, but since we have dx and dy, this is certainly true. That if you integrate over a curve in the positive direction, you get a value, but if you do the same curve but now in the negative direction, for dx or for dy, you get negative what you would have gotten otherwise. Also recall that if you take the double integral over two regions, if the integrand is the same, then this is actually going to be equal to the double integral over the union of these two regions. So assume those regions are not the same region and they have no intersection, the union of those regions compose one new region. So in fact, the way we kind of saw this is if you have this region D, that you can split up into two regions D1 and D2, then the entire region, let's call it D, is just equal to the union of D1 and D2. So to take the double integral over D, you can actually take the double integral over D1 and then take the double integral over D2 and add those two. So that's what this bottom thing we're recalling says. And now the general statement for Green's theorem, it's hard to write down in words, so all I can do really is just show you what the regions can look like in order to apply that formula for Green's theorem. And it has to do with orientations a little bit. So imagine we have a region D that has a hole. So there's a piece missing from it. Maybe not necessarily a circle, but definitely a piece missing. So the region D is this without the inside. Now, Green's theorem is actually still true so long as we have positive orientation on the outside, and this can maybe blow your mind a little bit, maybe not too much, but just a little bit, negative orientation on the inside. Why is that? Well, it's because we can take this so-called incision here and here, let's say, so that we actually have these two regions, D1 and D2. So D is being broken up to D1 and D2, much like it was here. But now, we now have these kind of two pieces, and you can kind of see that if you were to continue the orientation, it must be like this, and then like this. So just to show that, it's kind of hard to see, but just to show that, I'm going to attempt to copy this, but split up. So we have the top one. Okay, imagine that's the same, and then the bottom one. Something like that. Now, the orientation, if you just kind of imagine the arrows, here it's completely positively orientated. See that? And then here, for the bottom one, it's also completely positively orientated. Let me see how that is. So it's actually like this. It has to be this way, actually. So what you may think is that, well, I kind of didn't really do it justice when I explained it here, but here you can kind of see that, wait a second, these are in the opposite orientations. And that is certainly true, actually. So in green here, it actually goes each way for each one of them. In other words, these lines don't make a difference, because for these segments of these respective curves, they actually cancel out because of this. So since the integral over the negatively orientated one is equal to negative the integral of a positively orientated one, when you add them together, imagine adding this to the other side, you get that they cancel out to 0 over these regions here. So on these lines, we actually have cancellation. In other words, they don't actually matter. Now again, Green's theorem is true only if you have it like orientated like that, where the inside hole is oriented in the opposite way. And in fact, I think the same is true if you have multiple holes, and I can try to show that, but you can imagine viewing it with that incision in mind and keeping in mind the cancellation of things. Now the reason why Green's theorem is true is because we're essentially taking the double integral over two curves, or over two regions, D1 and D2. Now I say double integral because Green's theorem turns a line integral of one curve into a double integral over a region. So here we have curve, region, and we're kind of gluing it together to describe this curve and this curve at the same time. So I hope that makes sense, but all I'm really telling you is that you can apply Green's theorem to regions like this, so long as they're oriented like that. We'll do an example, so I know you're probably anticipating that. But now let me just describe what it would look like if there are more than one hole. So let's say we have two holes. Now let's imagine making this incision, and let's see if it's true that they both have to be, the inside both have to be orientated negatively. So let's see, so I'm not going to draw too many arrows here, but this is positively orientated, so counterclockwise on the outside. And then if we make an incision, let's say here, then we're going like this. And then we have to go either up or down, but then we have to continue like that. So if we go down below, then it's like this. If we go above, then it's orientated positively. So that's kind of the weird part. But we have to maintain the orientation here as well. So I don't think it actually matters, but let's take a look. So if we go above, let's say, then this can be orientated negatively, and then here, and then negatively. Yeah, there we go. So that totally makes sense. Because if you choose to go up and then down, I guess that can possibly work as well. But then one would be orientated positively and one negatively, and it gets kind of funny. But here, this way of doing it still makes sense. Notice that these lines, again, the orientation doesn't matter because we get cancellation there over those parts of the curve, because we get this so-called double overlapping of opposite orientated curves of the same curve. All right. So again, if you have holes in your region, you're not a simple connected region. That's fine, so long as the inside part is orientated negatively, but the outside curve is oriented positively. Can't say that enough. So now we're going to take a look at an example that will actually be an example involving a vector field. So let's see that example right now. Right, so for this example, we're asked to evaluate this integral. Well, really we're asked to show the integral will always be 2 pi for every positively orientated simple closed path that encloses the origin. Now what that describes is something like this. So any closed path C that encloses the origin. So encloses describes that it's a closed region, positively orientated because it says that, and encloses the origin just means it contains the origin. It doesn't actually pass through the origin, but it circles around the origin basically. Now, this is not what we're going to use directly. As it turns out, it's pretty difficult to do that, and the reason why is because the given vector field is not defined at 0 or 0, 0, because then the denominator would be 0 because x and y are each 0. So that's kind of obvious why that's the case there. In fact, the numerator would also be 0, which is curious because you may think, oh, it's 0 over 0, it's indeterminate, so maybe we can play around with it, kind of. But I'm not going to do that. Instead, I want to attempt to use Green's theorem, but we're actually going to need to use the general version we just described of Green's theorem, where we have a second curve that is, well, going to be a hole somewhere. And in fact, it's going to be a hole that encloses the origin as well. And as we'll be seeing kind of shortly, we actually need the insight to not be negatively orientated, but also positively orientated, which I know sounds funny, but just bear with me and I'll kind of explain why that's the case. So the first thing is that this integral, using Green's theorem, well, first we have to figure out what P and Q are. So if you, let me think here. So the integral, line integral over C or along C of this vector field dot dr, we know is just the integral along C of P dx plus Q dy, where P and Q are given by the vector field. So here, let me just say in red, that P is going to be negative y over x squared plus y squared, and Q is going to be x over x squared plus y squared. Now, there is something actually pretty special about this specific vector field where this scenario actually happens. And it actually becomes apparent once you apply Green's theorem. So assuming we can apply Green's theorem, let's kind of take a look at what happens. So applying Green's theorem, this becomes a double integral over some region D, which I haven't really described too much yet, but let's kind of do some exploration still, of Q dy. That's a little tricky to compute. You could use the quotient rule. There's something else we can use as well, but I want to see if we should, let's just use quotient rule. So for quotient rule for Q, derivative of this with respect to with respect to x. I keep saying that wrong, but yeah, you swap these, so Q is with respect to x now with respect to y. So with Green's theorem, remember that we swap the variable basically. So derivative of this with respect to y, we definitely need to use quotient rule. So derivative of the top is 1 minus, derivative of the top is 1 times the regular of the bottom, so that's just going to be x squared plus y squared, there we go, minus regular of the top times derivative of the bottom, and remember with respect to x, derivative of the bottom with respect to x is 2x squared, or I guess 2x, really. So when you multiply 2x by x, you get negative 2x squared, and if you combine x squared and negative 2x squared, that combines to just x squared. So really we have y squared minus x squared here. The denominator is going to be squared, because by quotient rule, it's all over the denominator squared. So that's nice. Minus the partial derivative of p with respect to y now. So derivative of p with respect to y, again, we have to use the quotient rule. So that's going to be derivative of the top, which is negative 1, times regular of the bottom. So it's going to be x squared plus y squared like this. If you distribute the negative, you get negative x squared. Trying to think what we can do. Well, we'll just leave it like this for now. Maybe we'll manipulate it after. But then minus regular of the top, which is negative y. So that makes a double negative y, which is positive y, times derivative of the bottom with respect to y is just 2y, because x squared goes to 0, so that's 2y. Okay, so now notice, if you distribute the negative here, what we end up getting is negative x squared and negative y squared. So let me actually just do that. Negative x squared, negative y squared. And similarly to how x times 2x was 2x squared, y times 2y is positive 2y squared, and look at that. Negative y squared plus 2y squared is positive y squared, so those combine like that, and it's all over the denominator squared, again because of the quotient rule. Perfect. And then dA. Now what you may notice is that you can actually make this positive by pulling out the negative, but notice that even worse, or maybe better, depending how you see it, y squared minus x squared is the same as negative x squared plus y squared. It's just a rearrangement. So if you rearrange this like that, then you get matching numerators, and since you have matching denominators, this is really something minus itself, which is 0. So the derivative of this, or not derivative of this, but the double integral of this expression using Green's theorem, so that's by Green's theorem, is actually equal to 0 no matter what d is. That's actually pretty important. The only problem, again, though, is that we can't actually include a region where a p and q are not defined. So we can't actually include the origin. So we have to make a hole there. Now, if we made it so that it was negatively orientated, trying to think how that would affect things. I don't think we'd have an issue there at all. Maybe we can just make it negatively oriented. Oh no, you know what? Yeah, I kind of see the issue now. Maybe there is no issue. That's fine. Let's just make it negatively orientated, because remember, by the general version of Green's theorem that we previously discussed, if the hole is negatively orientated for the boundary point, then this region D, the double integral over D is still valid. So that means that the integral, the line integral over C, but so this D is that D. So that means this C needs to be, well, the integral over C, let's call this outside curve C, but now this inside curve, we must call something else. So let's call it C1. So that's the one kind of detail I didn't describe earlier. I just explained what the region has to look like if there's a hole for the generalized version of Green's theorem. But basically what happens is that since these incision cuts, like I mentioned before, cancel out, really what we're doing is taking the sum of these two line integrals over these curves. But yeah, so here's the problem. The problem is that since this is negatively orientated, then this actually becomes a minus. So this is going to be negative C1 p dx plus q dy. And you may think, well, okay, integral of negative C1 is negative integral over C, but that doesn't necessarily mean they cancel, because C and C1 are different curves, they're not the same curve. They were the same curves, and yet they cancel out completely, kind of like what happened with the incision lines. But that's not the case here. So what we've actually shown is that the integral along C of p dx plus q dy is actually equal, if you just subtract this to the other side, negative the integral along negative C1 of p dx plus q dy. So notice that if you want to make this positively orientated, you can actually negate the whole integral, but since it's already negative, it makes it positive. So that's why I was kind of toying around with the idea of making the C1 positively orientated, because we end up getting from this idea here that the integral along C is equal to the integral along C1 if C1 is oriented positively. So these are both positively orientated closed curves, C1 and C. All right, so what does that exactly mean? Well, it means that for any curve C, we have it equal to this C1. Now, I didn't say what C1 was, I just said that it was a hole. Now, it can be any hole, as long as it's contained inside of C. Now, to ensure that it's inside of C, because we don't know how big C is, C can be huge, it can be tiny. So what we're going to say is that C is given by the curve, well, the set of x and y, set of points x, y, where x squared plus y squared is equal to, let's say, a squared. In other words, this circle, the radius a, where a is taken to be super small. So a can be any number really, but we want a to be small. So let's just say a small. So just imagine a is small. So now this integral is equal to that integral over this curve. And now we can parameterize So I'm going to parameterize x and y as being, well, a cosine and y sine. But to do that, I don't have space, so I'm going to erase for space, and we'll continue the example. Okay, so I've erased for space. It's kind of a crazy problem so far. I know the video is getting a little long, but here's what we discovered. The integral along C of the vector field f dot dr is actually equal to the line integral over this closed curve C, which is equal to the integral over this closed curve C1. C can be any curve, but C1 is a specific circle with radius A, where A is assumed to be pretty small as you need it to be, so that it is inside of that curve that's given, basically. Now we're going to parameterize this circle with x being a cosine and y being a sine. This is of course true because x squared plus y squared will be a squared cosine squared plus a squared sine squared, which is a squared times the quantity cosine squared plus sine squared. We've seen this before. Cosine squared plus sine squared is 1. So we just get x squared plus y squared is equal to a squared indeed. And t is acting as an angle here, so we're going to let it go from 0 to 2 pi to encapsulate the whole circle of radius a. So just to give you an idea of what the image looks like, we have any arbitrary curve C positively orientated, and then we have this small circle of radius a that is contained inside of that given curve. Okay, so now let's see if we can do it. So we want to do this. We want to evaluate this where x and y are given to be those, p and q are given to be those. Let's do it. So we know that now, since it's parameterized, this line integral is the integral from t equals 0 to t equals 2 pi of p dx. P is that guy. Negative y, that's going to be negative a sine of t. Notice x squared plus y squared is just a squared, so that's going to be over a squared. That's nice. But then we need dx. Dx is the derivative of x. Derivative of a cosine is a sine. Well, it's a times negative sine. And we actually have that here. So it actually will give us, let me just write it actually. But it'll actually give us positive a squared over times sine squared all over a squared. A squared's canceled. So this first term is really going to be sine squared of t. Okay, plus q dy. Q again is given by this. X is going to be cosine, so that's a cosine of t. So far so good. Over x squared plus y squared, again that's going to be a squared, as just discussed. And dy is derivative of y, which is a times derivative of sine is cosine of t, and this is all multiplied by dt. Awesome. Perfect, perfect, perfect. So now this, again, a times a is a squared. The a squareds cancel, so we get sine squared. This is positive. Also, these two a's cancel this a squared. So we get plus cosine squared. And just like we said before, we saw quite a bit actually in this video, this is just what? It's just 1. Perfect. So this is lining up just right. Now we can say the integral from 0 to 2 pi of 1 dt. Well, antiderivative of 1 with respect to t is just t. Evaluate between these limits is just the difference. 2 pi minus 0, which is just 2 pi. We have shown what was needed to be shown, so we're done. That's it for the video. I really hope we all enjoyed. I'll see you in the next video. Like always, thanks for watching, and I'll see you then.